Tonight I'm going to talk about open clusters, basically stellar clusters in general, with an emphasis on open clusters and asterisms. I love observing these objects for a very simple reason. No two of them are alike. A lot of objects that we look at in telescopes, galaxies, and some other things, they have very similar appearances, but open clusters are all different, and each one of them has its own unique appearance, and some of them are just absolutely beautiful to look at. Additionally, there are plenty of areas in open clusters and star clusters for amateur astronomers to make discoveries and to advance the science of astronomy. So there's a lot of good things that can be done as far as observing open star clusters. A talk on these objects would not be complete without mentioning Robert Trumpler. He is the grandfather, the pioneer behind these objects. He coined the term galactic clusters in 1925. He cataloged 37 new open clusters, which he discovered. He created a catalog of 334 open clusters in 1930. And one thing that made him famous is he finally determined what dark nebula were. William Herschel thought they were holes in the universe. Edward Emerson Bernard found that they were obscuring clouds, but he didn't know obscuring clouds of what. And Trumpler was able to determine that it was dust. So for that, he got a lot of fame and notoriety for discovering what dark clusters really are composed of. He also devised his Trumpler open cluster classification, which is still used today. And it's basically takes a group of stars and it measures them by concentration, brightness, and the number of stars. And additionally, if there's any nebulosity involved, he includes that as well. So I need to cover a few things to talk about from the science point of view, and do some explanation so that people can understand some of what I'm talking about later on. First off is radial velocity and proper motion. Stars, open clusters, all objects in our Milky Way galaxy and in the universe, in fact, are in movement. The stars that we're looking at, the open clusters that we're looking at, when we talk about radial velocity, we're talking about line of sight velocity. The object is coming towards us, it appears blue shifted. If it's going away from us, it appears red shifted. And from that, we can determine the distance of this star or this open cluster. And if we can determine the distance of the cluster, and we know its apparent motion across the sky, east to west, north to south, or whatever, if we can determine that, then we have two sides of a right triangle. And knowing that, we can develop the third side, which in trigonometry we'd call it hypotenuse, but that is the true motion of a star or an open cluster, and that true motion we call proper motion. And you will see a lot of proper motion studies during this talk. But this is how objects move within our Milky Way galaxy and within star clusters as well. This is a image of the Big Dipper as it looks today, and these arrows are the proper motion of the stars around the Big Dipper. But those stars in the Dipper are also moving in relation to the Earth, in relation to these other stars. And if we went back 50,000 years ago, this is what the Dipper would have looked like. This is it today. 50,000 years from now, the Dipper will be pouring out its water from the spout because these stars will have moved due to proper motion in this fashion. So these motions are so slow. They're measured by milli-arc seconds a year, which is 1/1000th of an arc second. So we don't see that visually. We wouldn't even see that in a lifetime. But over a period of time, say 50,000 years, you can see real movement of stars within our Milky Way galaxy. the distance that we determine based on radial velocity studies is very important, because we cannot do any of this without knowing the distance to these objects. And there's two ways of measuring distance. One is the cosmological Doppler redshift. If a object is moving away from us, it is redshifted. The spectral lines are shifted towards the red end of the spectrum. If it's moving towards us, the spectral lines are moved towards the blue end of the spectrum. And the amount of that shift will give us an indication of the distance. For closer in objects, and some methods that are being used with satellites today, which I will talk about, a big way of doing this is trigonometric parallax. They use the base of the Earth's distance from the sun, which the diameter would be 180 about 186 million miles, and you use that to figure a right triangle, and we can come up with a shift in stellar objects in the background. And you can see that if you hold up your hand in front of your eyes and you open one eye and close and blink back and forth, and you'll see the background behind your hand shift from one side to the next. That is parallax. And that's how we measure the distance to these stars. A shift in the background of 1 arc second, by definition, is what we call a parsec. That is 3.26 light years, and a parsec stands for parallax seconds. So this this is a very, very prominent means of measuring distances to stars in our Milky Way galaxy. But these are the two main methods of doing it. And as I say, distance is all important. We can't do any of this without knowing how far these objects are away. So it's either by Doppler redshift or by parallax. The big boost, the big increase in technology that we have seen was in 2013, where the Gaia Space Observatory was launched by the European Space Agency. This is rewritten astronomy as we know it. Most amateurs, or a lot of amateurs, are not familiar with the incredible work that this has done, because it doesn't take pretty pictures like the Hubble Space Telescope or the James Webb Telescope. But nevertheless, the information that is generated by this satellite is ever much as important as either of those two optical instruments are. It's absolutely awesome. There's no area in astronomy where Gaia has not had an impact. Currently, we're on the third edition of material that has been published. The latest one was the DR3 version that was published in June of 2022. And this enables us to measure the movement, the proper motion of stars in the background to an accuracy of the diameter of a human hair from 1,000 kilometers away. We've never seen that kind of accuracy before. In the past, we had to resort to photographs. Where a star was in 1954, where a star was on a photograph in 1964, so on and so forth. That's very inaccurate. This is extremely accurate to a level that we've never imagined before. The final edition will be a DR5, which will probably be issued somewhere around 2026, 2027. And with that, they will be able to measure the diameter of a pinhead on the surface of the moon from Earth. So this is incredible information that's out there, and it's freely available. It's on the website. Amateurs can access it. I access it all the time, and you'll see a lot of data on based on Gaia information. Currently, it's accessed about 2 billion stellar objects. It targets each star 140 times over a period of 10 years, from 2013 until 2024. And they're projected to run out at the end of this year. but the sensors are stronger and lasting more efficiently than they thought. So they might be able to extend it past the end of this year, hopefully. But it accesses 50 million stars a day, and it's simply incredible. And I'll show you a lot of data generated from Gaia. And here is some of it. Here's a true open cluster, Rosalind 3. And you can see the proper motion of the stars. And open clusters are formed out of the same nebulous cloud at the same time, and they're gravitationally moving through space together, which I will cover. But as such, their proper motions will be very similar. And you can see that is the case with Rosalind 3. The red arrows that are going off in anomalous directions, those obviously are not cluster members, but the yellow objects are. Historically, people have talked about the coat hanger, Roche's cluster. And the general idea is it's an asterism. It's a group of stars that are gravitationally unrelated. They appear to be together, but they're at different distances, and they're not moving through space together. But is it really an asterism, or is it really an open cluster? Well, Gaia answered that. Boom. Hardly any two of those stars are going in the same direction. So, yes, this is definitely a stellar asterism, a grouping of stars which appear to be related from our point of view, but in fact, these stars have nothing to do with each other, gravitationally or in proper motion, in movement. So that's the benefit, some of the benefit that we get from Gaia. It's also doing studies on 500,000 quasars and a lot of other aspects, too many of which to go into here. The Milky Way galaxy, the galaxy plane is very thin. There's a thin galactic plane and a thick plane. The thin plane is only 180 light years in thickness, along here, and this is where stars form. Stars form out of this gas and dust, and the material, the movement in here is very volatile. So most star clusters don't last but a few 100 million years, and then they dissipate and become single stars as they leave the cluster of stars. So most of your open clusters that you see most of your young open clusters are located along this thin galactic plane. There are some clusters which are older and they have moved away from the plane where there is less turmoil and less turbulence, and they can last for hundreds of millions, if not billions of years in time. So this is where we see the most of the open clusters, and when we look up at the Milky Way sky at night, that's what we're looking at. The sun oscillates around the galaxy. It takes the sun about 230 million years to revolve around the Milky Way. If you were to age the sun, it's made about 20 trips around the Milky Way galaxy so far. And this movement is sinusoidal. It moves up above the plane and below the plane. Right now, currently, we're about 55 light years above the plane of the galaxy, and we're moving upwards at 4.5 miles per second. The solar system, which is represented here, and this is not the scale, but this is the plane of the Milky Way here. Our solar system is tilted 63 degrees with respect to the plane of the Milky Way. This is why we see the Milky Way galaxy in the summer Milky Way and the winter Milky Way. In the summertime, we see the Sagittarius clouds. In the winter we see the Perseus clouds. But we can always see the Milky Way 365 days a year because of this axial tilt of our solar system with respect to plane of the galaxy. Our location in the galaxy is kind of obliquely away from the galactic bar. This bar has a length of about 17,000 light years, And there's some speculation that it may be a bar within a bar, but we're well positioned in order to be able to observe a lot of aspects within the Milky Way because we're between the two major spiral arms, the Scutum Centaurus arm and the Perseus arm. We're kind of right in the middle on what's called the Orion Spur. So this makes it convenient for us to observe objects within our Milky Way galaxy. Our galaxy has a diameter of about 180,000 light years if you figure in the dark matter. If you take the dark matter away, it's about 100,000 light years away. But astronomers are, including dark matter in most galactic diameters these days. There's about 400 billion stars in our Milky Way, and there's our sun is located about a little over 26,000 light years from Sagittarius A star. Sagittarius A star is what we call the 4 million solar mass black hole in the center of the Milky Way galaxy. Out of an estimated 100,000 open clusters, which astronomers figure our galaxy contains, we've only cataloged about 4,000. The reason for that is this dust and this gas. I mean, when we look towards the center of our galaxy, we have to look through the Scutum Centaurus arm. We have to look through the Sagittarius arm. And the dust in the galaxy blocks out our view and prevents us from seeing basically the other side of the galaxy. When we're looking through this, they call this the zone of avoidance, and it avoids just about everything on the other side of the galaxy. And for embedded clusters, for stars that have yet to form, that are in their birthing cocoon, we study those with infrared light and long wavelengths, radio wavelengths, so they can penetrate a little bit further in and through these gas clouds and dust clouds, so we can see a little bit more of the other side of the galaxy in areas we cannot see visually. But basically, we see only 5% through the galaxy in visible wavelengths, which is really not very much. We, in fact, can observe other galaxies much better than we can our own Milky Way galaxy in a lot of cases. There's something called the solar cycle. Our sun rotates around the center of the Milky Way galaxy about 27,000 light years out, and open clusters, star clusters that are interior to this, tend to get torn apart, and they don't last very long, a few tens of millions of years, maybe a few hundred millions of years. But the further in towards the center of the galaxy we go, the more turbulence we get, and the less the fewer open clusters, the fewer old open clusters that we tend to see. Your older open clusters are further out from what we call the solar circle, which is where our sun and we are operating. So one thing that people are questioning, how do we know how old a cluster is? How do we know the age of these objects? Well, this is the classic Hertzsprung-Russell diagram, and I don't have time to cover all of this because this is stellar evolution. But stars spend 95% of their time on what we call the main sequence. At some point, they use up their internal fuel via fusion, and they exit off on what we call the red giant branch. The larger stars, your more massive stars, will burn through their inner fuel much quicker than, say, your smaller stars. A class O star may last only 10 million years. Class B star, 100 million years. Class F star, 3 billion years. Our sun has a life expectancy of about 10 billion years. So we can use this to determine the age of an open cluster by knowing what the type of star is right here at the turnoff, because this, where these stars turn off the main sequence, they're the oldest stars in the cluster. And in this particular case, this is the globular cluster. This is a HR diagram for the globular cluster Messier 55. And at the turnoff point, we have K-type stars. And by spectral analysis, we determine those stars 12.3 billion years of age. All of the younger stars, the O stars, the B stars, the A stars, all of those stars have disappeared. They've either gone supernova or they've gone up through the red giant branch and they're no longer there. So just by knowing what type of star is at the turnoff, we can tell the rough age of that star cluster. And that is used constantly throughout astronomy to determine the age of these star clusters that we're going to talk about tonight. All right, when I was preparing for this talk, I ran across this picture, and this thing blew me away. Absolutely blew me away. This is a chart taken by the NASA Stratospheric Observatory for Infrared Astronomy. They ran constant studies for 4 years, and this is an image of our Milky Way galaxy. But these are polarization magnetic field lines that you're looking at here, and this is absolutely incredible because interstellar dust interacts with the galaxy's magnetic fields, and these magnetic fields will attract dust, and this dust will collect in polarized fashions in lined up to a point until it gravitationally gets large enough that it starts collapsing. And this gravitational collapse of this dust will form star clusters, open star clusters. So this is a picture of open star clusters before they even form, which is an incredible thing to be able to observe. These are pre-stellar objects, and it shows that our Milky Way galaxy is full of gas, full of dust, and it is building stars big time. Currently, about 7 stars are born each year in the Milky Way galaxy, and from the looks of this, there are many more to come. So this is an incredible picture here that I couldn't pass up without putting in this talk. All right, there are several groupings of objects that we call stellar clusters. There's open clusters, nuclear star clusters, superstar clusters, stellar associations, globular clusters, galaxy nuclei, stellar remnants, and asterisms. I'll try and talk about each one of these a little bit with the emphasis on the first one, open clusters. So what is an open cluster? I mean, here's a group of stars. It looks like a group of stars. Is it an open cluster or not? We'll try and determine just what makes an open cluster. Visually, as I said, all are different. This is probably maybe one of the most beautiful open clusters in the sky. It's Messier 11, the wild duck cluster. And right next to it is Aprimusvili 1, or Basel 1, which is a different type of open cluster. And these two clusters are so close in the sky, they're almost in the same field of view. But this is what you get when you look in the Milky Way galaxy in some areas, because it's just cluttered with open clusters, and you get magnificent ones and then some that are a little bit different right next door. But Messier 1 has a young age of 250 million years, about 2,900 members, and it has a total mass of about 5,000 solar masses. So this tells us that a lot of these stars are probably fairly small stars. There's a brighter star in the center, but there is no Gaia data on that star as to whether that star belongs with this cluster or not. My guess is it probably does, and this cluster is located inside the solar circle. Another definition of what defines an open star cluster is all of the stars, since they're born out of the same nebulous cloud, are the same age, relatively speaking. They also have relatively the same chemical composition. and they form out of the same cloud with the same chemistry. Only 10% of the cloud will coalesce in the stars before radiation pressure will remove the stars or remove the cloud. The the larger stars, the class O stars, the class B stars, the class A stars are extremely energetic, and they're throwing out radiation at a prodigious amount, and they will literally blow the cloud away and prevent further stars from forming. So this is it's rather unusual to get to see a young cluster with its birthing cloud still involved, but nevertheless, there's quite a few of them out there if you look for them. This is Rosalind 4, and it's only 10 million. The star cluster is only 10 million years of age, which is a baby. The next cluster is in Cepheus, NGC 7129, and here again, the birthing cloud. These are massive, massive stars. These are O-type stars, which are the brightest, most massive stars that there are, and they shine in a bright blue light, and that blue light is causing this blue reflection nebula. That the nebula is emitting the reflected light from these stars. 42% of open clusters are less than 100 million years of age. So most of them do not last, a good percentage do not last past 100 million years. And as such, they are close to their birthplace. These stars are in their birthplace. A good 13% of open clusters are greater than 1 billion years of age. And these are the more massive clusters that have been able to hold on to their members because of the sheer number of stars and the gravitational attraction that they impart. But it's nice to be able to see, as I say, it's nice to be able to see the star clusters that are still in their birthing nebula. All right, another aspect, what defines an open star clusters? Stars are at the same relative distance. They would have to be if they're formed out of the same cloud. And why is this particularly important? It's hugely important because the stars in the cluster that appear to be the brightest really are the brightest stars. The faintest stars emit the least energy. A lot of times when we look in the night sky, we have no perspective of if a star is brighter or if a star is fainter. Is that because the brighter star may be closer, or it may be a more massive star? We just don't know. A good example is Vega. It's the brightest star in the northern sky. It's only 25 light years away, which is why it's so bright, but it's only about twice the size of our mass of our sun. Deneb in Cygnus is a little over a magnitude fainter, but it's 60 times further away than Vega. And it is 19 times the solar mass. So this is a good example right here where we lose a perspective of what is bright and what is dim and why it is that way. When we look at an open cluster, these bright stars are really bright. They're brighter than that star, and that star is brighter than that star, and so on and so forth, because all of these stars are at the same distance. This is Messier 29. It's in Cygnus. It's a beautiful open cluster. It's only 10 million years of age, and the stellar masses are from 0.8 of a solar mass up to upwards of 100 solar masses. So these are very large, very massive stars that we're seeing here. And there's 50 members of them, and the diameter of the cluster is about 11 light years. This cluster is what we call visual eye candy. It's absolutely beautiful in any telescope. NGC 6910. Another definition: the stars are gravitationally bound, and the stars have proper motion, which I talked about earlier. For a cluster to be stable, astronomers have figured that the stellar density must be greater than 10 stars per cubic parsec. And remember, a parsec is 3.26 light years in distance. The internal gravity obviously must exceed the external forces trying to pull these stars out of the cluster. So this NGC 6910 is parked right next to Gamma Cygni. It's behind the Cygnus X cluster, which is the largest star-forming region that we know of in our Milky Way galaxy. And if we do the Gaia information, yes, it's a true open cluster. You can see the cluster members are all at the same proper motion, the same radial velocities, and they're moving together towards the southwest. The objects in red are non-members of the cluster, and you can see they're going off in different directions at different proper motions at different speeds. So this graphically shows, thanks to Gaia, that NGC 6910 is a true open star cluster. So a big part of open clusters is the classic open cluster definition. The stars stand out from the background. Those of you that have looked at some of these open clusters, not all of them do stand out from the background, but the ones that do are pretty spectacular. However, are the stars truly related, or are they a chance alignment? Here we have Ferraro 31. This is a beautiful Y-shaped cluster, and it is an asterism. Over here, we have NGC 2169. This is the famous 37 cluster in the constellation of Orion, and hopefully you can make out the 37 structure. But is it an open cluster, or is this an asterism? Well, when we do the Gaia information, yes, it is an open cluster. There are two anomalous members here. They're going off in the wrong directions, but the main members of the 37 are all moving in relation to one another with a similar proper motions. So yes, this is a true open star cluster, which is visible in most small amateur telescopes. You can see the small Dobsonian type telescopes. You can see the 37 number very, very vividly. It stands out easily from the background. All right, we'll talk a little bit about asterisms. I read an article, someone called them an incidental overdensity of stars, which I guess is a good description of them. But asterism, as I mentioned, are chance alignments. They're not gravitationally bound. They're at different distances. Some are foreground, some are background objects. They have divergent proper motions. And an asterism is anything your mind can dream up. Amateurs make discoveries of asterisms all the time. And I've included a couple of interesting ones here. This is Brochy 1, which is a perfect rectangle. This is a double star here. Dolids 9, the pistol, is an interesting cluster. Here's one that was discovered by Houston's Bram Weissman. It's called A for asterism, and it looks like he wasn't looking for it. He was looking for another object, but he just stumbled across this and says, wow, that looks like a perfect A. He was thinking about calling it spindle top or Mitchell's ladder for my 36-inch telescope ladder, but I think he settled on A for asterism. But you can see the Gaia data, no two stars are going in the same direction. So this, in point of fact, is a true asterism. There are a couple of catalogs out there by French amateurs, Laurent Ferraro and Prigiev Prescard, which the Ferraro catalog has about 50 asterisms in it. And these things are fun to look at. Some of them are very small and insignificant, but some of them are very nice. And they're just fun. They're just fun objects. And as I say, amateurs, this is an area that amateurs can make some discoveries and add to the science of astronomy just by using your imagination. When you're trying to find that galaxy or you're trying to find that nebula and you run across a little star cluster and it reminds you of something, jot it down, and you can turn it into the American Astronomical Society, and you may get your name on a discovery. You never know. Here is Kimball 2. It's a mini Cassiopeia. If you can see that, it looks just like the constellation Cassiopeia. And boom, no two stars are going in the same direction. So it's a true asterism. Stein 1, this is a very small grouping of 4 bright stars, and none of them are going in the right same direction. Their proper motions are all different, so a true asterism. Here's Napoleon's hat, which I showed this to the folks up at Stellafane, where I do an observing program. It looks just like Napoleon's hat, and the people up there went crazy over this. It's best seen in a finder scope because this is a huge object. But when you put the Gaia information on it, here again, no two stars are going in the same direction. So this again is a true stellar asterism of stars that appear to be related from our point of view, but in point of fact, have no relationship with one another gravitationally or motion at all. This is an interesting object, however. Messier 73. This is one of Charles Messier's objects of 110. And historically, this was considered an open cluster. Then it was downgraded to asterism. These 4 stars appear to be related, but are they or are they not? It's thought that initially there were 700 stars. Now there's only 11 in what's called an extended corona around here. I think there's a good case maybe made for the fact that maybe this, instead of being an asterism, maybe this is what we call a stellar remnant. Because if you put the Gaia data to it, this cluster is 2 to 3 billion years old. These stars are moving not identically in the same direction, but sort of. In the period of 2 to 3 billion years, there could have been some drift. The proper motions are similar enough that I feel like maybe this could be what we call a stellar remnant. A stellar remnant is a once large open cluster that all of the members have been cast away, except the denser, the more massive objects, which tend to sink to the center of the cluster. They are the only objects that are remaining of what was a much larger open cluster of stars. The kind of the gotcha here is the Gaia distances range from 1,000 light years to almost 2,300 light years, and you can see that these are the more distant objects. These would be the closer object. But again, in 3 billion years, maybe they could have drifted that much as well. I haven't read this anywhere other than just me talking, but I can see where there's a good case this may be a stellar remnant and not a true asterism. Messier 73. Stellar clusters have been discovered by amateurs. There is a Brazilian amateur, Bruno Alessi, has done a lot of work with open clusters and asterisms, and he's made a lot of discoveries. This is an asterism. This Alessi 62 is a true open cluster. Alessi J20046-1030, a true open cluster. And here's one of my Mac galaxies parked inside the open cluster right here. But this is a discovery that Bruno made back about 20 years ago. There's a couple of Austrian astronomers, Matthias Kronberger and Philip Tuch, who have made significant discoveries just by looking at photographs. the Digital Sky Survey, the two mass charts. Kronberger has 88 listed Kronberger objects, 41 of which have been certified as open clusters. And he did this just by looking at photos. Philip Tooch has 173 listed Tooch objects, 146 of which have been certified as open clusters. And while he was at it, he also discovered 50 planetary nebulae. So these are discoveries that have been made by amateur astronomers, just like us, and they just took the time to look at the photographic data and made themselves famous. So this is something that any one of us can do as well. Stellar associations. These are groupings of young stars that are weakly bound, or in some cases, they may not be bound at all. This is Cygnus X, which is located behind the Cygnus Rift. Excuse me. And this is one of the richest star formation regions in our Milky Way galaxy. And there are two basically stellar associations, Cygnus OB2, which has a whopping 2,600 class O and class B stars, the most massive stars that we know of. And this grouping is 10 times the Orion A complex. So that is huge. And then the Cygnus OB9 cluster, which encompasses NGC 6910, which we saw before. And this surrounds Gamma Cygni, which is the cross star in the constellation of Cygnus. So this is what we typically think of as stellar association: big, huge, loosely arranged groups of weakly bound stars. Although there are smaller stellar associations as well, and the Ursa Major moving group is a classic example, where these five stars are moving in this direction together, weakly bound, but they are moving in this direction, and the other two stars are moving in the opposite direction. There are three types of stellar associations: OB associations formed of massive stars, T Tauri associations formed of stars that have yet to form, and then there's R associations, which are reflection nebula, and of the three, these are the most commonly seen. These were discovered by Victor Ambartsumian way back in 1947. And so they've been around for a while, but only recently accepted. These stars, as they moving in general and in a loose configuration, will eventually form a stream of stars through the Milky Way galaxy. And by virtue of Gaia, here is our Milky Way galaxy. And this shows a lot of these stellar streams. As of 2021, there were 60 of them that are known. As these star clusters move through the Milky Way, they leave stars behind, and those stars that are left behind form the stream. There's been 6 major merger events that we know of in our Milky Way galaxy, going back to about 13 billion years. We have 170 globular clusters that we know of, although Gaia is adding to that number. And currently, there are 59 Milky Way satellites, which are scattered throughout and all around. So these are tidal streams from stars and from other galaxies that have merged with our Milky Way galaxy, also with globular clusters as they move through the Milky Way galaxy proper, through the heart of the galaxy. They leave a stream of stars behind them as well. So nuclear star clusters, these are the most massive star clusters in the universe. They typically have a mass range from 1 million to 100 million solar masses, which is incredibly large. Diameters up to about 32 light years. When we look at other galaxies, these small little faint fuzzies that have a brighter middle in the center, a lot of times that brighter middle in the center is light from the nuclear star cluster that's in the center of that galaxy. Not only are these star clusters very massive, but they're very bright. And they enable us to see detail in other galaxies. This is the nuclear star cluster in our Milky Way galaxy. Our black hole, Sagittarius A star, is here, which is surrounded by our nuclear star cluster. It has a mass of 1.5 million solar masses, the cluster does. It is obscured by 30 visual magnitudes due to the dust and obscuration between us in the middle of the galaxy and the spiral arms that are interior to us in the middle. Of interest is a star that goes by the name of S4716. It is the fastest known star. It whips around the black hole, whips around Sagittarius A star at a rate of 18 million miles per hour. And it revolves around the black hole, and consequently, its rotation rate around the galaxy is only 4 years. So that's how we know that there is a black hole there, because the radial velocity of that object is moving at an incredibly rapid pace, so fast that it should be centrifugally thrown out of the system because it's moving so fast. How much gravity does it take to keep that object moving that rapidly and that close in orbit around whatever it is in the middle? And that works out to be a black hole. Works out to be a black hole with a mass of about 4 million solar masses, which is what our Sagittarius A star has. So that's some interesting stuff about our nuclear star cluster. Unfortunately, being obliterated by 30 magnitudes, we cannot see it. But radio telescopes, infrared imaging can do that, and this is a near infrared image taken by the Very Large Telescope of our nuclear star cluster. There are another type of star clusters called superstar clusters, and these are everywhere throughout our Milky Way galaxy, throughout other galaxies, and these are progenitors of globular clusters. This particular one here is the Arches star cluster. It is named the Arches star cluster because it's located in Sagittarius the Archer, and it is the densest star cluster that we know of in the Milky Way galaxy, the densest being the most closely packed stars in the interior. And someone figured if the sun were as populated as the Arches cluster, that would be 100,000 stars between us and Proxima Centauri. Proxima Centauri is only 4 light years away. So that is a bunch of stars that will be packed in that 4 light year span of distance if we had the density that the Arches star cluster does. There would be no nighttime astronomy observed if we were inside of this cluster, by the way. The Arches cluster is 85 light years from the black hole. It is extremely young, only 2 to 4 million years of age. It has a cluster mass of 70,000 solar masses. The largest star that they know of is 130 solar masses, and it's estimated the largest star that our present epoch is capable of making is about 150 solar mass stars, although we don't know of any. But there's 100,000 stars packed into a very small amount of space. And again, the visual extinction is about 30 magnitudes because of its location in our Milky Way galaxy. Another superstar cluster is Westerlin 1. This is in the southern hemisphere, in the southern constellation of Ara. And this is an open cluster that is actively forming a globular cluster. Its age is also very young, only 4 to 5 million years, has a mass of 50,000 solar mass, and it's very faint. Its brightest star is 20.5 magnitude. But these superstar clusters are massive objects. But a truly massive object is Omega Centauri in the southern constellation of Centaurus, which is a stellar object at the Texas Star Party every year. I mean, this thing is just absolutely gorgeous to see in a telescope. And for years, there was some doubt as to its true nature. Is this a globular cluster? If so, it is a humongously big globular cluster. Well, Gaia has settled that argument. It is not a globular cluster. It is actually the nucleus of a dwarf galaxy that merged with our Milky Way galaxy about 100 million or about 10 billion years ago. And the galaxy had a mass of about 100 million solar masses. Currently, there's 10 million stars, and it has a mass of 4 million solar masses. It's the most massive cluster in our Milky Way galaxy, but it's not a true cluster because this is, in fact, the galaxy nucleus. It has an intermediate sized black hole in the center. And the reason it's able to retain this and why we know that it is a galaxy nucleus is its orbit is highly inclined. So it dives almost perpendicularly through the plane of the Milky Way galaxy. And as such, very few stars are separated from the galaxy proper. There's another cluster in our Milky Way galaxy, which we think is also a galaxy nucleus, and that's Messier 52. It's thought that it is the CD or the host cluster for the Sagittarius dwarf spheroidal galaxy, which is currently merging with the Milky Way galaxy. So this, as I say, this is a galaxy nucleus, and it's a beautiful, beautiful object in just about any telescope. So difference in open clusters versus globular clusters. There's some stark differences. Open clusters are loosely structured. Globular clusters are tightly structured. I won't go through all of this, but open clusters basically have a single generation of stars. Those stars formed one time out of that nebulous cloud, and they are moving through space together, as I mentioned. A somewhat recent discovery is that globular clusters have multiple generations of stars, and they use something called the sodium-oxygen anti-correlation to find this, where sodium is enhanced at the expense of oxygen. That tells us that the enhancement of sodium came from a pre-existing generation of stars, and it depleted their oxygen in order to form this new generation of stars. So when we see this sodium oxygen anti-correlation, we know there are multiple generations of stars. And since open clusters do not have multiple generations of stars, this has become the defining criteria as to separating a globular cluster from an open cluster. However, in astronomy, as well as with most sciences, there's always exceptions. And here we have Berkeley 46, and they don't know what to call this because it's got multiple generations of stars. Some aspects acts like an open cluster, some aspects like a globular cluster, and some of these larger clusters have this problem. So this is still being worked out as to the difference between the different types of stellar clusters. So stellar clusters and star-forming regions can be seen in other galaxies, which are visual in amateur telescope. I love doing this kind of stuff. It's really nice to be able to see detail in other galaxies. And I'm going to run through some of this pretty quickly. But this is NGC 4038, 4039, the antenna. These are H2 regions. H2 regions are where stars form out of this ionized hydrogen gas. And these particular regions are very young, 5 to 10 million years, 13 million years, 5 million years. They're very young, but they're very obvious and obvious to see in just about any aperture telescope, which is interesting because these two galaxies are merging at a distance of 45 million light years. Now, that's a fur piece down the road to be able to see detail in another galaxy. NGC 4038 is a gas-rich spiral galaxy. NGC 4039 was a gas-poor spiral galaxy. These two galaxies started approaching one another about 900 million years ago. 600 million years ago, they passed completely through each other. And 300 million years ago, the tidal tails were ejected from the galaxies as a result of the merging. And the most recent merger event of which we're seeing a lot of this activity was 5 million years ago. 400 million years from now, this will become one galaxy. But these star-forming regions are interesting. They're almost iridescent when you look at them in a telescope, and they're well seen from the Texas Star Party. I mean, this galaxy is absolutely gorgeous from the Prude Ranch in Fort Davis and the dark, transparent skies that we have out there. However, this is looking at H2 regions. With this galaxy, you can actually see some open clusters. These are super star clusters, which I talked about. But these are not just any old super star clusters. There's 14,000 point-like objects scattered throughout the galaxy. Many of these are young globular clusters. I have noted a few of them, of which I am pretty sure I have been able to see through my 20-inch telescope. The published information says that these star clusters are 17th and 18th magnitude. Don't ever go by published magnitudes because they're brighter than that. You'll see these pinpoints popping in and out of view, which we call stellarings. And if you see it, our rule is if you see it 3 times in the same place, you saw it. You know, catalog it, consider it done, and you can see these star clusters, individual superstar clusters in this galaxy. But the reason is the mass of these objects. The mass of these superstar clusters are 2.5 to 4.7 million solar masses. I mentioned Arches, the largest, most massive superstar cluster in our Milky Way galaxy is only 70,000 solar masses. So these things are huge. I mentioned Omega Centaurus has a density of 4 million solar masses, and that's the core of a galaxy. Well, some of these have the same mass as the core of that galaxy. So these are huge, huge star clusters, and within these two galaxies. And if there are astronomers over here looking, they would have one hellacious night sky to enjoy when they're looking at these two galaxies in their sky. NGC 4214 is another object which can be, the objects inside can be seen through amateur instruments. This is a large complex of H2 regions, 213 light years in diameter, very young age, 3.5 years. The NGC 4214-2 complex, this is the youngest complex, the most energetic complex in the galaxy. You can see this fairly easily in amateur instruments and this as well. And of interest is IVS. That is a single superstar cluster, which you can see in this galaxy. This is in the Canis Venatici group. So it's about 40 to 50 million light years away. So that is a huge star cluster there that can be seen as a separate object. And you see 4449 is one of my favorite objects. You could easily spend a night just looking at all of the detail within here. All of these H2 regions are visible in amateur instruments. This is a star here. But this is a nuclear star cluster, which is very bright. Probably the brightest feature in this whole galaxy is the nuclear star cluster right here. Um, and this is a rapid star formation in these areas, and it cannot last. This galaxy is a dwarf galaxy. It's going to use up all of its gas in a short amount of time. But right now, we know of 61 individual star clusters, and so far 14 globular clusters that are over 9 billion years of age. And about a year ago, some of us from our observing site in Central Texas were looking at one of these globular clusters in this galaxy in Keith Rivich's 25-inch telescope. So it's nice to be able to see that kind of a detail in something other than the Milky Way galaxy. And all of this detail is easily seen, I would say, in down to 12-inch aperture telescopes. Messier 82, a lot of people look at M82, but they never really look at M82. These different groupings of these are all individual star-forming regions, H2 knots. This is a starburst galaxy. This is turning out stars within these clouds at a prodigious rate. The A cluster here, which is seen here in the visual, this is the B cluster here. These are easily seen in almost any telescope. This V-shaped dark lane is very visual in amateur instruments. And these clusters are 600 to 20 million years of age. They're very young. And they're rotating separately within the galaxy itself. Of interest is E, F, and particularly H, this one right here. That is a single superstar cluster. This is the highest surface brightness of any known star cluster right here. It has been reported as a supernova numerous times, and it can be seen in moderate-sized telescopes. It's 15th magnitude, so it requires a little study, but it's right on the lip of this dark lane. And if you see that, you're seeing a single superstar cluster located in another galaxy. Messier 101 has 10 NGC objects within the galaxy itself. These are all star-forming regions, superstar clusters, and they're fairly easily seen. The NGC 5461 has 12 clusters located within this group. 5462 has 33 H2 regions, and you can kind of see the individual knots there at 25 clusters, and there's a black hole in the center of this. The one that I like the most is 5471, this one here. In my telescope, it looks blue. And there's some controversy in whether it is a member of Messier 101 or whether it is a separate galaxy. But it is very bright. It's 200 times the size of M42, and it's kind of off to one side, but it is very easily seen. And to me, it looks like a separate galaxy. Like I say, it's bluish in color. But that blue color is due to the fact that there is a hypernova, a very massive star that went kaput, that went supernova inside, and it created that blue structure. So the jury is out as to whether this is a nebula or a separate cluster. But all of this detail, these are NGC objects inside of M101 that can be seen in amateur telescopes. So I'm going to look at a few objects which I love. This is probably my favorite open cluster, NGC 7789. It's called Caroline's Rose because it was discovered by Caroline Herschel back in the 1780s. And it is a very rich cluster, as you can tell. And it's also a very old cluster at 1.6 billion years of age. It contains approximately 1,000 stars, and it is famous because it has a type of star known as a blue straggler. And I have marked some of these blue straggler stars. These stars are 12 and 13th magnitude. They're not faint. They're not difficult to see, but they're interesting. And there are 30 of these blue straggler stars that are known to exist within NGC 7789. Blue stragglers were discovered in 1953 by Alan Sandage, and they're still debating as to what these objects are to this day. But the prevalent idea is that it involves two different stars that either formed collisionally into one star, or it was a double star that merged into one star. And what happens is we have two old stars. After they merge, they get spun up. They start rotating at a higher rate of speed, but since there are two stars, they're more massive stars, and they appear to be younger in age. And if we plot these on a Hertzsprung-Russell diagram, they're beyond the turnoff point. They're where stars should not be, but nevertheless, they are there. And that's the conundrum, because how do we explain this? And the best explanation is it's two stars that merged into one, and these are now the most massive stars that are located in the star cluster. And as I say, they're discovered because of their position on the HR diagram, but also because of their rapid rotation. Our sun rotates in about 27 days or so. Stars, as they age, they tend to slow down their rotation rate and get slower and slower. These stars here in Messier 55, these stars are rotating at around 30 days or so. These stars are rotating 10 to 12 in 10 to 12 days. So that's a standout blueprint spectroscopically for not only where they're positioned, but their rotation rate. And there is another type of stars which they've more recently discovered called blue lurkers. These are rapidly rotating stars, but they're two stars that were of a smaller size, smaller density that merged, and they're also rotating at a more rapid rate than other stars on the main sequence, and they call those blue lurkers. There are 42 blue straggler stars in our Milky Way bulge, and they're finding more and more of these objects at a place where they really don't belong. Mercury 46, one of my favorite clusters. I could do an entire talk on this object. This is one of the most unique oddball objects in the entire universe. Berkeley 46, or NGC 6791. It's the oldest open cluster we know of. Its age is 8.5 to 10.2 billion years of age. That is ridiculously old for an open star cluster. Yet, its metallicity is twice that of the sun. Metallicity is a term that astronomers use for anything that was not made in the original Big Bang event of the universe. 13.8 billion years ago, the Big Bang created hydrogen and helium. And a few 100 million years after that, the first stars were generation 3 stars, and they were formed almost solely out of hydrogen and helium gas. They lasted only a few 100,000 years or a few million years because they had densities of hundreds of solar masses, so they didn't last very long. But when they went supernova, they created the metals. Anything heavier on the periodic chart than hydrogen or than helium was considered metals. And everything that we see, every hard everything that we have here on Earth, us included, everything is considered by astronomers to be a metal, and as such, they were created in the heart of stars, and as such, that took millions of years for that to happen. Our sun, the metallicity of our sun and our Earth and us, it took about 9 billion years for that to form, because our sun is 4.5 billion years of age, which is, and our Earth is 4.5 billion years. So it took about 9 billion years for the metals to form in our solar system. Yet Berkeley 46 formed twice as many metals in less than half the time, in only about 5 billion years, because its age is 8.5 billion years. Astronomers have argued back and forth that can't possibly be, but they finally decided on the answer, and is staring us right in the face. The sheer number of stars, the mass, the gravitational attraction of all of these stars, which at one time was about 400,000 solar masses of stars, that when those generation 3 stars went supernova and they created all of those metals, the metals couldn't go anywhere because of the gravitational field. So the next generation of stars was highly enriched in metals. And that is the current best answer as to why we have something as old as it is, but yet it has twice the metallicity of our sun. Its orbit is also highly eccentric, which is how Berkeley 46 is able to hold on to the stars that it has. And currently, we know of 75 blue stragglers within the cluster, and 4 blue lurkers. So currently, it's considered an open cluster, but it could be a globular cluster or it could be a galaxy nucleus. There are strong arguments for either of those 3 classifications, but there's more. It has 3 generations of stars within it. Instead of the standard single generation of stars, there are 3. And that is proven by the sodium-oxygen anti-correlation, which is very strong within this object. And these white dwarf stars are cooling over a period of time. There's no internal flames or anything inside these white dwarf stars. They're just cooling down. It takes billions and billions of years for that to happen. Well, they found out that the white dwarfs in Berkeley 46 are unlike white dwarfs of any other cluster. These white dwarfs have helium cores. They never went through something called the helium flash, so they're very slow to cool down, and those are stars that are 6 billion years of age. Stars that did go through the helium flash, that have the classic carbon cores, the white dwarf carbon cores, those are 4 billion year old stars. Then stars at the tip of the main sequence, these are 8 billion year old stars. So this is very, very odd. I mean, it's, as I say, it's still considered an open cluster, but it's 3 generations of stars here, which is not what you would expect with an open cluster. And a lot of these have to do with these under massive stars. When we do the HR plot, it took me time to do this, but you can see all of these stars are going in the same direction. They're all gravitationally bound. There's a few outliers, but mainly everything is in conjunction with its being an open cluster. There's one other area which I'll just touch on real briefly, but there is a blue horizontal branch of stars over here. Metal rich stars should have all red horizontal branch stars. So these stars don't belong here either. So hopefully this gives you a general indication of just how screwed up Berkeley 46 is. I mean, there has been countless papers written trying to explain away this odd object, which is faintly seen in a telescope, but it is one of the true interesting objects in the night sky, and well placed for observing right now. NGC 188 is another very old cluster. It's up around the north polar regions. Its age is 4.7 to 7 billion years of age. It has 35 blue stragglers, although Gaia has only accounted for 24. And it is a very old, spread out cluster. On the night sky is 2 times the size of the moon's diameter. NGC 6520 is an absolutely gorgeous open cluster. It looks like a flower with a bright star in the center with the flower petals around it. And it is parked right next door to one of the darkest dark nebula in the sky, Barnard 86. And there was some speculation that this Barnard 86 is a Bok globule. Stars are forming within this dark cloud that possibly NGC 6520, which is right here, formed out of the cloud. Well, they have found that the true proper motion, the true space motion of these two objects are very dissimilar. 6520 is approaching at 23 kilometers per second, where Barnard 86 is approaching at 11 kilometers per second. Therefore, they did not have the same origin. So this is basically two ships passing in the night. But we now know, thanks to Gaia, that this star cluster did not come out of the Bok globule of Barnard 86. However, when we look, is this star a member of the cluster? Well, when we do the Gaia data, it's kind of messy, but you can see there it is. So it's the same as the other members. There are some outliers, some members with some non-members, anomalous objects, which are going at a very high proper motion in opposite directions. But essentially, this is a true open cluster, and the bright star in the center is a true member of that open cluster. Another beautiful cluster is the Tau Canis Major cluster. Here we have another example of a bright star in the center, surrounded by a much fainter grouping of stars. This is a very bright, beautiful, beautiful open cluster located at a distance of 5,000 light years. It's a very young cluster, only 4 to 5 million years of age. And the question for years has been, is Tau Canis Major an actual cluster member? It has a visual magnitude of -4.4. I mean, it's a naked eye object. And it's a supergiant type 09 star. But does it have anything to do with these other stars? Well, actually, yes, it does. It is at the same distance. It's moving with the other cluster members. As a true cluster member, it's just a massive, massive object. But being a O-type star, it has a life expectancy of maybe 8 to 10 million years. So that also verifies the fact that this is a 4 to 5 million year old cluster. Because if this was a 20 million year old cluster, that bright star would not be there because it would have already gone supernova. So this is more of the wonderful information that we're getting from Gaia. And one of the favorite objects that a lot of amateurs look at, particularly at star parties, is NGC 457, or the owl cluster. To me, it looks more like an owl, but a lot of people call it the ET cluster because of the two bright stars. This is the brightest open cluster in the bright constellation of Cassiopeia. It is at a distance of 7,900 light years. It is a little bit older cluster. It's 21 million years of age, and it consists of 60 stars. And to me, if these are the eyes, this is the body. You can see the tail kind of fans out, and to me, these are the wings. But most people see this, as I say, as ET. But the idea is one Phi Cassiopeia and two Phi Cassiopeia are these foreground stars, or are these actual members of the rest of the cluster? And in point of fact, yes, they are. They are true members of the cluster. They're moving in the same southwesterly direction as the rest of the star clusters. There are a few anomalous stars that are involved, which have nothing to do with it. This one has a very high proper motion going in a general easterly direction. But you can see that these two members are cluster members. The number 1, 5, is one of the brightest stars that we know of. It's brighter than Rigel. Actually, it is a very, very bright, massive star. And 2, Phi Cassiopeia, this is a very bright variable star. I think it's 4 NGC 457, 456 is the name of the star, and it's a bright variable star. So that's some information about open clusters, which I enjoy observing, and hopefully most people will generate an interest in these things as well. As Don mentioned earlier, I do have a book coming out. This is what I think it's going to look like, although I've not seen a copy of it yet. But it's scheduled to be published in November. I will be glad if it's done by the end of the year. But if you enjoy the talk about these objects that I've been talking about, and learning a little bit about what each one is, well, that's what this book is all about. I show you how to star hop, how to find the objects, and then I tell you something interesting about each one of the objects, with the idea that if you look at some faint fuzzy thing and you don't know anything about it, it's just a faint fuzzy thing. But if you know that it's 125 million light years away, and it's got Wolf-Rayet stars, and it's sending off supernova, and it's performing, if you know something about it, then that makes it an interesting object. So that's what I've tried to do with this book. A final thought, and I like to end up my talks with a quote from the great amateur astronomer Leslie Peltier. He was probably the greatest amateur astronomer, and he once suggested a cure for many of the world's problems is simply one gentle dose of starlight to be taken each night just before retiring. I hope I believe most of us would agree with that 100%. I have tried to put together a little grouping of open clusters, which will hopefully give you an idea of why I enjoy observing these beautiful, wonderful objects, and hopefully it will spur you to maybe do the same. I would end up with NGC 7789 and Cassiopeia. So I hope, as I say, I hope this spurs you folks to get out under the night sky and observe some of these wonderful objects that are bright and easily seen in most amateur telescopes. And with that, I thank you for your attention.
All right. Thank you very much, Larry. Do we have any questions for Larry? If you let's see if we have any in the chat. Larry, Bill Spazeri had a question. He wanted to know if the Pleiades M45 did those stars come from the gas cloud that can be seen surrounding them, or no?
Actually, no. They thought for the longest that the Merope cloud, which is the brightest one, that those objects formed out of that cloud. But they've recently found that that cloud was there in the beginning, and the cluster drifted into it. But the Pleiades did not form out of that surrounding cloud.
All right, great. Does anyone else have a question? That's the only one I could see in the chat. But if anyone else has anything else they want to ask Larry, you're welcome to. Anybody else? Okay. Well, thank you, Larry, for that wonderful presentation. And we always enjoy having you here to listen to you speak. Just thank you for all of us for being here. We appreciate having you in the club, and I remember when I was a kid out at the dark side with my dad, and you were out there doing your thing, and it's always great to talk to you and hear what you have to say, Larry.
I remember your dad well.
Yeah.
Very, very nice man. And thank you, Stephen. Thank you very much. I enjoy doing this, and like I say, I hope this spurs someone to get out into the night sky and look at some of these objects. But thank you guys again.